In the previous video, we took the encrypted file and we extracted two attributes from it, one of which was the EFS or the logged utility stream attribute. In this video, we will look inside the EFS attribute and see if we can extract the encrypted FEK from that. Now let's look at the steps. The logged utility stream is actually a binary data structure. And to examine that, it would make sense to open it up in a hex editor. I'm going to open it up in a hex editor called 010 editor. The logged utility stream will have an encrypted version of the FEK for each user that has access to the file. The best way to extract the EFEK for a user is to parse this blob of hex into its constituent data structures. So where can I find the data structures that are part of the logged utility stream? Microsoft does not publish this, so I would probably have to reverse engineer it, right? Thankfully, NTFS is a 25-year-old file system, and I did not have to put in that effort. I found the answer in opensource.apple.com, where they have an open source implementation of NTFS. The structure of all the NTFS attributes is defined in a file called layout.h. At the bottom of this file, I found exactly what I was looking for, which is the structure of the logged utility stream attribute. Once I found these structures, I took them and created a template that can be used with the 010 editor. I have this template posted on my GitHub page. If you want to use it, you are more than welcome to do so. If you are not sure what is the template and how it is used, I have a playlist in my channel that talks about what are binary templates and how you can build simple templates for the 010 editor. You can take a look at it if you are interested. Now back to the topic. I'm going to run the template that I created on this logged utility stream.bin file. Once the template runs, I am able to see the data structures present in this file at the bottom of the screen. I'm going to select a DDF record, and here I can see an encrypted FEK field. If I go to the next DDF record, I can see the encrypted FEK here as well. And likewise for the DRF record. In this case, I am actually looking for the encrypted FEK of the test user, which I presume will be the first one. But just to check, I can zoom into the public key details structure, and when I select the username, I see the test user here. So that is confirmation that DDF record 0 belongs to the test user. Now let's get the corresponding EFEK. To do that, I will right click on the EFEK, go to selection, and click on save selection. This will allow me to save the EFEK in a separate file. Let me open up the saved file in the 010 editor. So this is my encrypted FEK. If you look at the size of the EFEK, it is 256 bytes or 2048 bits. This is so because the EFEK was created by encrypting the FEK with a 2048-bit RSA public key. Now, one of the most important things to remember here is the EFEK will be in Little Endian format. So you need to reverse the bytes to get the actual EFEK. There are multiple ways of doing this. You can do it in 010 editor as well. But for a change, let's use CyberChef. In CyberChef, I select Open File as input. Then I click on the file name. In the operations, I search for Endian, and there is an operation called swap Endianness. I'm going to add it to the recipe, and I need to change a couple of inputs. The data format will be raw and the word length will be 256 bytes because this is a 256 byte structure. I do this and then I click on bake. It gives me the output here. I'm going to save the output file and I will call it EFEK reverse.bin. I know this step can be slightly intimidating. So before going further, let us stop for a moment and take a look at what we have accomplished here. We looked at the logged utility stream attribute, which was a bunch of hex, and we have extracted the EFEK or the locker for the test user. Now to open this locker, we need the private key of the test user, which is what we are going to get in the next step.